So let's look at ionic bonding first. So let's draw Lewis symbols for potassium and for chlorine. So the symbol for potassium is K. How many valence electrons does potassium have? 1. It's in group 1. And the symbol for chlorine is Cl, and how many valence electrons does it have? 7. So 1, 2, 3, 4, 5, 6, 7. I'm putting them in pairs, top, bottom, right, and left. Exactly where you put those pairs doesn't matter, but don't draw them all on one side or make a circle of them because it's hard to look at. Is potassium happy? Does it have an octet? No. Is chlorine happy? No. Chlorine has 7 valence electrons. It wants 1 more to get an octet. Potassium has 1 electron. So we might think, well, potassium needs to gain 7 electrons. That's a lot of electrons. There's an easier way for potassium to have an octet. Here's the electron configuration for potassium. Here's that 1 valence electron. If we get rid of that, having a brain fart here. If we get rid of that, like that, now these are the valence electrons, right? So it's like I peeled off that partial layer of an onion skin, and now underneath is this beautiful, full, complete onion skin. And that makes the atom happy. It has now become an ion by doing that. I'll put that back. So we remove 1 electron, it becomes a potassium ion, but now it has an octet underneath. We don't draw those electrons as dots in the Lewis structures. The only ones we show as dots were the original valence electrons. So what we do here is we say, well, potassium transferred its electron to chlorine. The chlorine's like, man, I just need 1 electron and then everything would be good. Life would be awesome. And potassium's saying, I got to get rid of this electron. But you can't just leave electrons on the side of the road. You have to find somebody to take them. So these guys get together and they cooperate and make each other happy. So what we end up with is potassium with no valence electrons in the diagram, but we understand that if you lose all the dots, that means you have a full octet underneath. And then the chlorine is now going to have 8 valence electrons and a -1 charge. Traditionally, conventionally, we put brackets around the anion Lewis structure, and we write the charge on the outside. The most obvious reason I can come up with is that negative can very easily get lost in all those dots, and so by putting the charge on the outside, it just makes things clearer. We don't usually do that for potassium because there's no valence electrons showing, and so that the plus doesn't get messed up. Mastering chemistry, they have not figured out how to do brackets yet. They do all kinds of crazy stuff in that program. They don't do brackets. So please do not text me asking how to put the brackets on chloride ion. You just have to leave them out. So just so you know that. Any questions? What's going to happen with a positive ion and a negative ion? They're going to be attracted to each other. They're going to stick together like magnets, and that forms an ionic bond. So the ionic bond forms by 1 or more electrons being transferred from a metal to a nonmetal. Now they're charged, and they stick together electrostatically. Okay, let's use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. This is not how you would do a problem like this on an exam or something. We already learned to predict the formula, right? But we're going to see what the electrons are doing here. So this is just kind of an exercise. So magnesium. How many valence electrons does magnesium have? 2. And then let's use a different color for nitrogen. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. They want octets. We have a metal and a nonmetal, so the nonmetal is going to gain electrons, the magnesium is going to lose electrons. So this magnesium is saying, I have to get rid of these 2 electrons. Hey, anybody want some electrons? And this nitrogen is saying, yeah, I need electrons, I need 3 of them. Magnesium says, well, I only have 2, but you can have them. And they're like, well, okay, that's better than nothing. I bet you didn't know that atoms talk to each other like that. So we can take those 2 and give them to nitrogen. Is magnesium happy? Yeah. Magnesium also has a charge on it, so we should do that. 2 plus. The nitrogen also has a charge on it now. What's its charge? 2 minus. Is the nitrogen happy? No, not quite. It's happier, but it hasn't gotten its octet. It only has 7. What to do? Where there's 1 magnesium atom, there's probably another one. So bring in another magnesium atom. It's got 2 valence electrons. The nitrogen says, hey, hey, can I have one of those electrons? Magnesium's like, yeah, please, take it. I want to get rid of it. So now, the charge on this nitrogen is 3 minus. It's happy. The charge on this magnesium is plus 1. Is the magnesium happy?
No.
Nope. What do we need?
More nitrogen.
More nitrogen. Okay, so here's another nitrogen. Nitrogen atom, 5 valence electrons. It's like, give me that electron. Magnesium's like, please, please take this thing. Okay, so now we've got 2 plus charge on the magnesium, and we've got nitrogen with a minus 1 charge. We've got 2 happy magnesium ions, 1 happy nitrogen ion, and 1 unhappy nitrogen ion. We need another magnesium. So I'll write him over here, and he's got 2 valence electrons, and the nitrogen's like, oh, I'm so glad to see you. You've got 2 electrons you want to get rid of, right? Yeah. Oh, please, give them to me. So the magnesium's like, great, I'll give those to you. There you go. Now this is a 3 minus charge. This is a 2 plus charge. Everybody's happy. But it took 3 magnesium atoms and 2 nitrogen atoms to get the right ratio to trade the electrons and transfer them. So looking at the formula, we're going to need 3 magnesiums and 2 nitrogens. So the formula will be Mg3N2. We learned how to do that kind of by magic before, just looking at charges and crisscrossing. But this explains better what's really going on. Any questions? We know from experiment that the formation of ionic compounds is usually quite exothermic, meaning a lot of energy is released. If we look at the formation of sodium chloride from sodium and chlorine, for every mole of sodium chloride that forms, 411 kilojoules of energy are released. That's a lot of energy. Where's the energy coming from? Well, sodium has an ionization energy, right? It's 496 kilojoules per mole. If we have 1 mole of sodium, then we have to give it 496 kilojoules of energy in order to pull that electron off. So that's something we have to put in. The electron affinity for chlorine is minus 349 kilojoules per mole. This is half a mole of Cl2, which is the same as 1 mole of just chlorine atoms. And so when we give an electron to chlorine, we get a release of 349 kilojoules. But when we add those up, we see that transferring an electron from sodium to chlorine actually absorbs 147 kilojoules. It does not release 411. So there's something missing in there. It's not just the ionization energy and electron affinity. The missing thing is the lattice energy. That's the energy associated with the formation of a crystalline lattice of alternating cations and anions. When we quantify this, it's measured in comparison to the ions in their gas state. So potential energy is lowered when opposite charges come together. We made a sodium ion and a chloride ion. That required an investment of 100 and something, 49 kilojoules. But now those charged particles come together, and the coming together of them releases energy. That energy is released as heat. I often personify atoms and ions. I'm going to say, well, metal atoms want to lose an electron. But that's not why they do it. It actually, they're not going to give up their electrons. You have to pay them for it. Nonmetals want to gain electrons. And it's true that a lot of the electron affinities are negative. They will pay you for an electron. But when you add that up together, it's not enough of an energy change for the compound to form. The compound forms because the transfer of the electrons and then the attraction of those oppositely charged ions is much lower in energy. And so we get this energy released when the cations and the anions stick together. So this is an illustration of that happening. Here we have sodium ions and chloride ions in the gas state. They're going to be attracted to each other. And they will very naturally, without any interference on anybody, you don't need to do anything or organize them, they will organize into this pattern. Because this is the maximum amount of attraction. It's the lowest potential energy. It's like rolling a boulder down the hill. You don't have to do anything to get it to go to the bottom. It'll do that naturally because it's lower in energy. And so that amount of energy that's released here is called the lattice energy. Well, it's very difficult to measure lattice energy. The easiest way to calculate it is using what's called a Born-Haber cycle. And this is a hypothetical series of steps that represent the formation of an ionic compound from its constituent elements. So this gets back to what we learned about in Chapter 6 with Hess's law. This tells us that the change in energy is a state function. And so it doesn't matter how you got there. It's just the difference between the beginning and the ending. And so we're going to use steps that we know the energy change for, and we can add them all up. So we're going to use steps where we know the standard heat of formation, and then we also need to know the overall change in enthalpy from the elements to the final ionic compound. That's pretty easy to measure. You can do it with, a bomb calorimeter or something like that. So here's an illustration. So we're looking at the formation of sodium chloride. We're looking at sodium metal and chlorine gas. Those are their natural states at room temperature. And we want to know the lattice energy that's released when sodium ions in the gas state and chloride ions in the gas state come together to form solid sodium chloride. We can't measure this. We can measure, though, the enthalpy change for the formation of sodium chloride from sodium and chlorine. That's just the standard heat of formation, forming 1 mole of this from the elements in their standard states. So to get this, number 5 here, we're going to use this overall enthalpy change, and we can also measure, other people have measured it, we can just look it up. The formation, the energy required to form gaseous sodium from solid sodium. So taking solid sodium and making it into a gas, vaporizing a metal. You got to put energy in to do that. And then we're going to take the chlorine molecule and split it into chlorine atoms. And that requires energy. And then we're going to ionize that sodium atom that's in the gas state, and we're going to make it a sodium ion in the gas state. That also requires energy. And then we're going to look at adding an electron to the chlorine to make chloride. That's going to be negative because the electron affinity for chlorine is negative. And so we can take all of these things and add them together and subtract this, and we get this difference, and that's the lattice energy. And so even though we can't really directly measure it, we can determine it by knowing these other steps. Any questions? There are some trends in lattice energies. Ionic size has an effect on the lattice energy. If we look at these chloride compounds, lithium chloride, sodium chloride, potassium chloride, cesium chloride, these are the lattice energies. These elements, the cations here, are all group 1A alkali metals. So we're comparing similar metals. What we see here is that as we go down the column in the periodic table from lithium to cesium, the lattice energy becomes less negative. So cesium chloride releases less energy when it forms than lithium chloride. And we can explain this in terms of the size of the ions. So here we have pictures. Each of these involves a chloride ion. The chloride ions, of course, are all the same size. But the cations are different in size. The lithium ion is the smallest. The cesium ion is the largest. Coulomb's law says that the energy, the potential energy, is proportional to 1 over the radius, the distance between these two objects. And so as the distance between the objects becomes greater, the attraction is less. We see this with a magnet on the refrigerator and a piece of paper. The magnet sticks to the fridge very nicely. Put 5 sheets of paper on the fridge and try to get the magnet to stick. Depending on how strong the magnet is, it might not stick anymore. Why? Did we kill the magnet? No, the sheets of paper are putting too much space between the fridge and the magnet. When we increase the distance from 241 up to 348 picometers, that's like adding pieces of paper between the magnet and the fridge. The force of attraction is less. The lattice energy is the energy that's released because of the lowering of potential energy due to the attractions. So larger ions, lower attraction. Does that make sense? We also see an effect of ion charge. Coulomb's law says that that energy is also proportional to the charge on the two objects. So if we have a +1 and a +1, or +1 and -1, or +2 and -2, the one with a +2, -2 charge is going to have 4 times as much potential energy difference as the one with +1. So here we're comparing sodium fluoride and calcium oxide. And these were chosen because the distances between the two ions are very similar. 231 versus 239 picometers. So there's not a significant difference in the distance. But we do see a big difference in the lattice energy. Sodium fluoride involves a +1 and a -1 ion. Calcium oxide is +2 and -2. And this is in the ballpark of 4 times larger. Any questions?
What would it be for lithium chloride?
Well, for lithium fluoride, lithium is a little smaller than sodium. So we could predict that the lattice energy for lithium fluoride would be a little larger than this, but it would still be smaller than calcium oxide.
Because they use that for nuclear reactors.
Do they?
The molten salt reactor, something like that. I don't think it's very good.
Yeah, molten salts are used for lots of things. but I'm not familiar with the details of the nuclear reactors.
I think they use it to carry them, like I said.
You can use it to carry electric current because molten salts will conduct electricity. And it'll be at a very high temperature, and so you don't have to worry about your wires melting, right?
To take that heat away too.
Yeah, they'll also conduct heat. So, trends in lattice energies. The lattice energies become less exothermic with increasing ionic radius, and they become more exothermic with increasing magnitude of ionic charge. This is like some of the predictions we did on the periodic table. There's a limit to what you can compare just on trends. And so you you can't look at both of these at the same time. You have to look at one or the other individually. So here's an example. Arrange the following in order of increasing magnitude of lattice energy. So increasing magnitude, that means we're going to start with the smallest lattice energy and we're going to go to the biggest. So we're going to go from low energy to high energy. Well, how does the distance between the two ions affect it? Like if you had a large distance between the ions, would that be high energy or low energy? Low energy. So this would be large radius, large distance. And then charge, higher charge will give us a larger magnitude, right? Higher plus minus. So here we've got lithium bromide, potassium iodide, and calcium oxide. Well, do two of these compounds have charge in common? The first two, right? Lithium and bromine both have a 1 charge. And potassium and iodine both have a 1 charge, plus 1, minus 1. So we could compare these on the basis of radius because the charges are the same. So let's find lithium and potassium in the periodic table. Here's lithium and here's potassium. Which one's bigger? The potassium. Potassium's bigger. So larger cation, probably lower energy. And then let's look at the anion, bromine and iodine. Here's bromine, and here's iodine. Which one's bigger? Iodine. Bromine's smaller, iodine's larger. So the two largest are the potassium and the iodide, and those are together in this one compound. And so the lithium bromide must have a smaller radius than the potassium iodide. Do you see that? Now, if it was lithium iodide and potassium bromide, then we'd have a problem. It would be harder to predict. So I can say that the potassium iodide is going to have a lower energy than the lithium bromide based on size. How do these guys compare to calcium and oxygen? Well, the sizes, here we've got calcium and here we've got oxygen. So the calcium is bigger than the lithium and the oxygen is smaller than both of those, but the charge has a bigger effect than the radius because you've got the charge of both of them multiplied. So Q1, Q2 for these two is going to be -1, and this is -1. For this one, Q1 times Q2 is +2 times -2, which is -4. There's a lot stronger attraction between the calcium and the oxide. there's not a real clear difference in size, but there is a big difference in the charge. The charge is usually going to have a bigger effect than the size. So is the calcium oxide going to have a higher potential energy, a larger potential energy, or a smaller? Higher. So I'm going to put calcium oxide here at the top. These types of questions show up on exams. Some students find them very challenging because you have to evaluate and compare multiple things.
So oxygen is always the strongest one?
Well, oxygen will not necessarily always be the strongest one. What if we had aluminum nitride, +3 and -3? +3 times -3 is -9. So that would probably have a larger magnitude of potential energy than any of the others, right? So what you have to do is compare 2 at a time and then put them in the order. Any questions? So it's always good to ask, does our model actually explain what we observe in reality? We observe that ionic compounds have high melting points. We observe that ionic solids are non-conductive, and we observe that solutions of ionic compounds, I'm missing something there. Ionic compounds is behind here. Compounds. Conductivity of ionic compounds. Ionic compound solutions, I think, is what's missing. Ionic compounds in solution are conductive. No, I need to talk about it here. So the reason that ionic compounds have high melting points is that those bonds, the ionic bonds, are non-directional. This cation is attracted in multiple directions to the anions around it. And so there is a very strong cohesiveness to the compound as a whole. And that's why it takes a lot more energy to cause it to melt and to break some of those bonds. Because those ions are held next to each other in a particular pattern, they're fixed in place, an ionic solid will not conduct electricity. If you melt it, though, now the ions can move relative to each other. We have charged particles that are able to move, and we see that the compound will conduct electricity. When salt dissolves in water, the ions become free to move, and the light bulb goes on, the solution will conduct electricity. So the Lewis model explains these properties of ionic compounds.